All right, welcome back. So I said in the last problem that I didn't know how to solve this using the techniques that we need from this section. And let me explain what I mean by that. So we're going to look at areas in polar coordinates, okay? Okay, so you may remember like from pre-calc, if you took that, that arc length and or arc length of a section, yeah, of a section of a circle was S equals R theta, and area of a section of a circle was A equals 1/2 R squared theta. And in both these cases, theta is in radians. Okay, so now all we do for this area is we're going to make the polar area, or the area in polar coordinates, is basically what we're measuring. It's a little bit different than what we measure in Cartesian. What we're measuring is if we have some curve here, we're measuring the area, some curve here. We're going to measure this area, okay? So how are we going to do that? What we're going to do is we're going to say, okay, well, we split it up into little sections, as we already have. We say this angle is d theta. Okay, so the area, or the dA, is 1/2 r squared of theta d theta. Okay. All right, so let's take, for example, a very sort of the trivial, the essential example, let's call it. Circle of radius 1 r equals 1. Let's do another one because we're going to look at that one later. So for r equals 1, that's easy. I know what to do with that. I just take the integral from 0 to 2 pi, 1/2 r squared of theta d theta, which is going to be the integral from 0 to 2 pi, 1/2 d theta, which is going to be pi. That's the area of this circle. We already knew that. Okay, now let's look at the problem we had before. Okay, so the problem we had before was this area. Okay, so now when we do the problem of the intersecting areas, I have to find this area by thinking about it as a polar graph. So I want to think about it as like the area from here to here. Okay, that's actually a much harder integral. I have no idea how to set that up in polar coordinates. Okay, now maybe I could come up with it. but I'm hamstrung by the fact that I know how to solve it in Cartesian coordinates. Okay, that's always sort of a danger in doing things different ways. Okay, but let's look at one that I can't do that way. Okay, so let's take a look at, this is number 8, and we're going to find the area enclosed by r equals sine of 2 theta. Okay, good luck trying to find a Cartesian graph for that. Good luck. That's all I'm saying. All right, let me show you why. Let's draw the picture of it first, and then you'll see what happens. So we're going to graph it. We're going to go do the Cartesian graph first. So r equals sine of 2 theta. That has a period of pi, but we're going to do all the 2 pi. So let me actually make that a little longer. Okay, so we're going to go to 2 pi, but it has a period of pi because of the 2 theta, right? So that means like so, dot, 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 and it repeats. Okay, so this is, of course, now pi over 4, pi over 2, 3 pi over 4, 5 pi over 4, 3 pi over 2, 7 pi over 4. Okay, so this is the Cartesian graph. Now, let's look at what the polar graph looks like. It's actually like that. A little more centered. Okay, so here this is r versus theta, but now we're going to do theta as actually the angle. Okay, so at 0, at theta equals 0, at theta equals 0, r equals 0. Fine. At theta equals pi over 4, r equals 1. That means that in this direction, we're going to be out here. And at theta equals pi over 2, it's at 0 again. So that means it's going to go a loop, like so. Okay. Now, what's going to happen from pi over 2 to pi? Pi over 2 is here, pi is here, but look, between those angles, my r value is negative. So that means I'm going to be in the 4th quadrant. Oh man, that means I'm going to have a loop over here. Actually, I think it's really cool. I'm not frustrated by that at all. Okay. All right, next, from pi to 3 pi over 2. So that's from this angle to this angle. It's going to be positive r value. So it's going to go out in the direction of those angles. So we're going to have a loop over here. Okay. And then finally, from 3 pi over 2 to 2 pi, that's these angles. But the r's are negative. That means it goes opposite direction. So I'm going to have a loop over here. Okay, so if you're having trouble, that's okay, I understand. Let's just think about this sort of like a certain given point, okay? So let's just look at pi over 4, for example. At pi over 4, you're out in this direction, and it should go in the same direction, right? So it should be here. All right, let's look at 3 pi over 4 with negative 1. 3 pi over 4 is this direction, but the -1 is going to mean you're looking at this point here. Okay. 5 pi over 4 with r equals 1. 5 pi over 4 is this direction. And that's this point. And then 7 pi over, that should have been 7 pi over 4, not 7 pi over 2. 7 pi over 4, that's this direction with a negative r value, so that means it's going to be this point. Okay? All right, that's not super necessary, but it's good to know. Let's now find the area enclosed. Well, that's not bad. We're going to take our area is going to be, now I'm actually going to do this, I'm going to say it's 4 because I've got 4 petals, and I'm just going to find the area of 1. Okay? Remember the formula for area, 1/2 r squared d theta. So the integral from 0 to pi over 2 1/2 r squared. But what's r squared? R is sine of 2 theta. There's that sine squared I was just telling you about in the other video, right? So that's 2, integral from 0 to pi over 2, 1 minus cosine 4 theta divided by 2 d theta. Again, this is an easy enough integral to evaluate. I'll let you guys do that, okay? I'll see you all in the next video.